I want to shift gears for a minute and go back to models of the atom. We've talked about two briefly already. The first one was the Dalton solid sphere model of the atom, right? You got this atom that consists of basically nothing, right? It's just a solid sphere, nothing inside it, nothing smaller than the atom itself, just a solid sphere. And then we talked about the Thompson plum pudding model of the atom, which was way, way, way off of what we currently believe the atom to look like inside, but at least it was an acknowledgement that there was something inside. Remember, Thompson was a sea of positive charge with a bunch of little electrons floating around inside it. That came from the cathode ray tube experiment, the discovery of the electron. I'm going to tell you about an experiment right now that was performed by a guy named Rutherford and his associates, his assistants, that led us to, I don't know if I want to say an evolution or a revolution in our understanding of how the atom works. Okay, Thompson was definitely a revolution, the idea that there was something inside the atom. Okay, he's going to take that though, and Rutherford, that is going to take that idea and turn it into something that looks much, much more like we currently believe the atom to look like inside. So the gold foil experiment involves something like this. We get this box that contains radioactive material that will release alpha particles. We don't have a box of alpha particles. We have a box of something, uranium-235, something that will release alpha particles. These alpha particles leave the little hole in the box, and they go towards this really, really, really thin piece of gold foil. It's kind of like aluminum foil, except it's, like tin foil you put on a turkey when you cook in the oven, except it's made out of gold and it's even thinner. Really, really, really thin. Now, these alpha particles, they leave this box one at a time and go towards the gold foil. And there's three things that happen to them when they hit the gold foil. By the way, we know what happens to them by virtue of where they hit this screen that surrounds it. We call it a scintillation screen, a screen that glows when charged particles hit it. So if a charged particle, an alpha particle, hits it right here, we know that it hits it right here because it glows at that spot. If it hits it back here, we know that it hits right there because it glows at that spot. Three observations Rutherford and his assistants make when they fire these alpha particles at this gold foil. The first is that the vast majority of these alpha particles, most of the alpha particles, go straight through. The vast, vast majority of them go straight through. If there's 110 yards in a Canadian football field, if I line 110 people up every single yard, I blindfold them, and I say and I direct them across the football field so that they're aiming in the right direction. And one by one, I say, you, number 27, go. Okay, the vast majority of people that are walking across the football field blindfolded will make it straight through to the other side if they're directed in the right direction. Okay, most of the alpha particles go straight through, but some of them don't. Some of the alpha particles are deflected. They change direction. They still make it to the other side, but they change direction. So it's like those 110 people lined up on the football field, aimed, directed toward the other side, but something, when they get to the middle of the football field, something causes them to change direction. They still make it through, they still make it to the other side, but if they start on the 30-yard line, they don't end up on the 30-yard line. They end up on the 45-yard line or whatever. So some of them don't go straight through, some of them are deflected, but most of them do go straight through. There's a few of these alpha particles now, very few, but still a few, bounce back. Like this. This would be equivalent on the football field to, maybe 2 or 3 of the 110 people directing them across the football field. They're walking across, and all of a sudden, they bounce back. They never make it to the other side. They end up not exactly where they came from necessarily, but in the vicinity where they came from, certainly the same side of the football field where they came from. Most of them go straight through. Some of them go through and change direction. A few of them bounce back. What did these three observations lead Rutherford and his assistants to conclude? Well, the conclusion that came from this one is that most of the atom is empty space, just like most of the football field must be empty space, right? If 100 people out of 110 go straight across the football field, then there must have been nothing in their way. So most of the football field must have been empty. If most of these alpha particles go straight through the goal, then most of the atom must be empty space. Some of the people that are walking across the football field make it across, but they make it across not straight across, not straight through. What does that tell us? Well, there must have been something that pushed them away from their straight line path. I'm walking across the football field, and all of a sudden I change direction. Something pushed me away from my straight line path. What's going to push a positively charged alpha particle away from its straight line path? Think about what I just said. What's going to push a positively charged alpha particle away from its straight line path? Or something that's positive, right? Okay, so there must be something that's small. How do we know that it's got to be small? Well, because most of the atom is empty space. There must be a small positive thing in the middle. We'll call it a nucleus. Thompson gave us the discovery of the electron. Rutherford gave us the discovery of the nucleus. There's got to be a small positive nucleus in the middle. A few of the alpha particles bounce straight back. So I'm walking across the football field. I don't make it across at all. I bounce back and end up on the same side as I started with. What does that tell us about that small positive nucleus in the middle? Well, let's say there's somebody in the middle of the football field that's pushing these guys away from the straight line path. What it means in number 3 is that I probably hit that person. Instead of just going close and being pushed away, I probably actually hit the person and bounced back. But what do I know about that small positive person in the middle of the football field? I know it's not a 2-year-old or a 3-year-old. Why? Because if I was running across the football field and I hit a 3-year-old in the middle of the football field, then hold on for a sec, then what would probably happen? I'd probably knock him out of the way and keep going, right? What does it tell me? It tells me that the person in the middle of the football field is bigger, heavier, right? Not bigger in size, but heavier. Almost done here. So here's Rutherford's model of the atom. We have a small, heavy, positive nucleus with electrons orbiting around it. This is a big deal. Although it's not, arguably not as big as Thompson, the idea that there's something inside the atom. Thompson was the first guy to say that, really, right? But this is still a big deal because it's the first acknowledgement of the general structure that we currently believe is the case, a nucleus with the electrons orbiting around it. All right, remember your homework for tomorrow is page 819. We'll check those over tomorrow. We'll have a quiz on fission fusion on Wednesday.